Today we have the last and final section of the syllabus. What are you going to do today? Today you're going to be calculating eigenvalues using numerical techniques, okay, for the square well. That's what you're going to be doing today. So you're going to be doing it in two methods. You're going to be doing it using two methods. One is your bisection method, and the other one is your Newton-Raphson method. Okay, so first, how I'll do this is I will tell you a bit about what you have done in your first semester, about the quantum square well and the types of quantum square well, so that we can use the results from there. And then we will take those results and apply numerical techniques that you've learned in your second semester, which is the bisection or your Newton-Raphson, and then we will proceed forth with trying to find the eigenvalues. Okay, so let's just start off with this. Okay, so what are we going to do now? We are going to, first, we're going to look at why we need to do this whole thing. Okay, then I will talk about the review that I mentioned earlier. And now, after that, we will look at the numerical methods that we can use for the energy, to find the energy eigenvalues. And then we will do the same problem using these two methods that we have, the bisection and the Newton-Raphson method. Okay, so why do we need these trial and error based methods? So these are not a set procedure method. So let's take an example of a matrix where you need to multiply two matrices. Okay, so if you need to multiply, say, two matrices, A, B, C, D, E, F, and say you have A prime, maybe, A prime, B prime, C prime, D prime, E prime, F prime. If you want to multiply two matrices, you have a set procedure. What do you need to do? You take the first row and you multiply it with this first column, and then you add all of those respective elements up. So you have a set procedure to do this. So you don't have to look into, okay, fine, let me try and input this particular initial value, initial guess, and then get the value from that. You don't have to do that. So these kind of procedures are for your set procedures. Okay, so how is it different? Basically, when we try to multiply two matrices, we have well-defined procedure. Okay, so you just have to repeat this same well-defined procedure in order to get your values. But then you have other algorithms which are trial and error based. So you go through a particular numerical procedure, and then you stop only when your error is, very little or small, and so on. Okay, now this, what is interesting here, it's basically, when you look at trial and error based method, what's interesting is that these are just like your experiments. So when we looked at Newton's law of cooling, we assumed the temperature of the surrounding to be something like 85 or something, right? No problem. So what is that 85 basically would tell you how soon you would cool off. So say your surrounding temperature was pretty much less than 85, you would have you would only take a lesser amount of time. So basically the trial and error based methods are interesting because just like your experiments that you do, it depends on initial conditions, and therefore this exact solution that you want is a little bit more harder to find out. Okay, so as you alter your initial conditions, the results that you get altered. So let's look into a standard problem in quantum mechanics, okay, which is the quantum states in a square well. So the most standard problem that you have here is your one-dimensional square well, right? So let's say you have a square well potential, okay? So of width, let's say the width is about 2a. I want you to look at this particular figure a bit carefully because there's a question that's coming up on this particular figure, okay? So what do you have? You have a potential you have a potential that's mentioned as V naught here, okay? So be a little careful. Look at this particular thing carefully. Here you have a minus a and a, okay? And you have x going this direction. You have your potential that's depicted in your y direction, okay? So I want you to look at this carefully for about 2 seconds, because the next question that I'm going to be starting off is based on this, okay? So I told you there is a minus V naught, which is the well depth, okay? The depth of the well. There's a minus a and an a here, okay? So let's now go to the pole. I'll start off a pole now. before that, let me just read this out. What kind of a square well did I show in the previous slide? Is it an infinite asymmetric square well? Is it an infinite symmetric square well? Is it a finite symmetric square well or a finite asymmetric square well? Okay, what are the two things that you have to look at? Is it infinite or finite? And is it asymmetric or symmetric? So let me just show you the diagram again. If you want to look at it again, you see a minus a and an a here. You also see the depth as V naught. Okay, so the potential well helps the depth V naught. So let me just start off this pole. Okay, pole number 21. So please plug in your answers. I hope you can see the pole. What kind of a square well did I show in the previous slide? Is it an infinite asymmetric square well? Is it an infinite symmetric square well? Is it a finite symmetric square well or is it a finite asymmetric square well? This is something that you have done in your first semester quantum mechanics class, so you should be very thorough with that. These are all the essential basics of the whole thing. Okay, 30 seconds left, so please plug in your answers fast. $20 seconds left. $27 of you have voted out of 45, so I'm hoping people will start voting faster. I'll wait for 10 more seconds, then I'm ending the poll. Okay, I'm ending the poll now. Okay, I'm going to share you guys what you have responded. Okay, many of you said infinite symmetric square well. Okay, majority of you said that. And finite symmetric square well. So one thing is clear, you guys get to know how to identify symmetric. Okay, so you have a minus a and a on both sides, so you know that that is a symmetric. So none of you clicked asymmetric, thankfully. Now, what about infinite and finite? I told you that the depth of the potential is V naught. Okay, it is a finite value. It's not V naught is equal to infinity, right? So the depth of the potential that I told you is V naught. Okay, let me just stop sharing the results and go back to the picture that we have. This is minus V naught. Okay, the depth of the potential is V naught, and you're not saying it's V is equal to infinity. So if your V is infinity, then it would be infinite potential well. Other than that, if I tell you that the depth of the potential is V naught in particular, this is finite. Okay, finite. Now, minus a and a, you have it on both sides of your axis, of your y-axis or the potential axis. Therefore, you have symmetric. How will an asymmetric potential look? The asymmetric potential will look like this. Okay, so let me just draw this here. This is V, this is X. Okay, and I will take a different color so that you can understand that clearly. So let's say, okay, I need to erase this part out. This wasn't very clear. Yeah. Okay. So you have a potential well like this. Then you do say this is minus V naught. This is 0. And let's say this is A. So it's not symmetric. It's not on equal sides to the V axis. Therefore, you say this is asymmetric. Okay. And this guy here, you have equal sides to both the sides of your V axis. So you say this is symmetric. I hope you get this clearly now. Okay, so now we're done with this poll. Now, this is like a precursor to what I'm going to be explaining. So even if you don't get this right, or if you do get this right, it's fine. But you should, in all things that are taught to you beforehand, you should be able to answer this question from your first semester classes. Can we have both bounds and scattering states for an infinite square well? Can you have both bound as well as scattering states for an infinite square well? Is it yes, no, or maybe? I will start the poll now. Okay, just a second. Let me take poll number 22. Yeah. Can we have both bound and scattering states for infinite square well? Why are you guys voting so slowly? 10 seconds are already up. These are things that you need to know beforehand. Somebody answered maybe. You usually don't go with maybe, okay? Whenever questions are given to you, they might put an option, say maybe, or possibly both, or something like that. You usually don't go with those kind of options. It's very rare those options are true. 20 seconds left for you guys to vote in. I'll give you 5 more seconds and I will end the poll. Okay, I'm ending the polling now. So I will share those results with you. Majority of you guys said yes, okay, by one person. It's almost like 50-50. Can we have both bound as well as scattering states for an infinite square well? When you're talking about an infinite square well, what are you saying? The well that you have has infinite depth. So how can you come out of the well? Okay, how can your particle come out of the well? Okay, so that's a question that you're supposed to be asking, right? When you have an infinite square well. So let me just explain this whole thing to you before I tell you what the answer is exactly. I hope I've stopped the sharing. Stop sharing results. Okay. So let's come back to this after I explain. Okay. So let's look at this. These are the types of square well that you can categorize your square well into. So when you're talking about your square well, it can be a finite square well or an infinite square well. Infinite square well basically means that you're trapped inside say a box. Okay, so your one-dimensional, your particle in a box is basically an infinite square well potential that you're using. Here you have your finite square well. Okay, and it can be symmetric or asymmetric. Even this can be symmetric or asymmetric, but the idea is that the particle can come out of the well. So then you have scattering states that are there. If your particle is stuck inside the well, you have bound states that are there. Okay, so in your infinite square well, your particle is stuck inside. Okay, unless suppose you have quantum tunneling or stuff like that, which happens. You have bound states that come up. Okay, over here. So let me just show you the results of what you guys have written again. Okay, so can we have both bound and scattering states for infinite square well? No, we cannot have both bound and scattering states. Scattering states only happen when you have a possibility that the particle can jump out of the well. Okay, so these are things, let me just stop sharing the results. These are your basics that you need to know. So I thought I would just cover them because a lot of you guys must be confused about this. Okay. So what are we going to do today? We are going to be solving a finite symmetric square well. Okay, so we're going to be calculating the bound states for a finite symmetric square well. We're not going to be looking at scattering states. We're only looking at bound states. Okay, so how can you write this? You can basically write this potential as a step. It's like a piecewise constant function. Okay, so you have minus V naught and you have 0, the other, when you look at x greater than or equal to a. Okay. Now, what are bound states and scattering states? So a particle with energy less than 0 will be in a bound state. So if you have E less than 0, the particle is confined to a bound state. And what are the nature of solutions? So the nature of the solutions are supposed to eat discrete energy states that you have, or your discrete energy spectrum. And the wave functions will decay in the regions where you have x less than minus a and x greater than a, but they oscillate inside that potential well in this region that you have. So here it would be oscillatory, if you have your bound state, and here you would have decaying exponentials. Here too, you would have decaying exponentials. Okay. Now, what about your scattering states? So a particle with energy more than 0 will be in a scattering state. So your E is greater than 0. So the particle is not confined here. And the scattering of the particle by a potential occurs, okay, by the potential that you have. So in this case, your wave function is oscillatory for all three regions that I mentioned earlier. So it's going to be oscillatory in region 1, region 2, and region 3. Okay. Now let's look at the wave functions of the bound state solutions. Okay. So the finite potential well that we looked at here is symmetric. Okay. So symmetry here can be exploited to reduce the calculations that you have. So you would have two different classes of wave functions. So one of them would be even, one of them would be odd, and you only have to choose a particular type to calculate, or a particular category to calculate your eigenvalues. So in the question, they would mention calculate it for an even wave function or calculate it for an odd wave function. So you don't have to do all the calculations that you need to have. So what you have here is there must be a wave function here. With well-defined parity, you would have odd or even functions. Okay, so you would have a sine class and you would have a cosine class. So you would have two different classes and they do not overlap. Okay, so the solutions are independent of each other. They do not overlap. Okay. So what we do here is we would take what you possibly would have done in your first semester. We're not going to be doing the whole derivation here. We're just going to summarize the important points from there. What you would have done is you would have had an even and odd wave function separately. And for bound states, the even and odd solutions always have different energies. So they are non-degenerate states that you have. So there's no degeneracy that you have. And there is no eigenstate, which is a linear combination of both sine and cosine. And this I mentioned again earlier. I told you that you could not have the same classes at the same time. Okay, so you could either have one class, you can have your sine, or you could have the other class, you could have your cosine class. Okay, so this I think you should know. What do you mean here by your even parity, your even wave function? These are not the wave functions that you actually see in the problem. Let me make that very clear. These are not the wave functions. These are just illustrative. Okay, so it's just to give you an idea of what you mean by even or odd parity. Okay, so here you have an even parity wave function against an odd parity wave function. Okay, so this is how it's going to be looking when you say even and odd. Now let's come to things that you actually need to remember. Okay, so this wouldn't be the equation that I show you next, wouldn't be the format that you have done it in your first semester. Okay, the equation that I show you next is not the format that you would have done it in your first semester. In your first semester, what you would have basically done would be either graphical solutions. I'm sure you would have done graphical solutions because you can't really use numerical techniques and write the whole problem down in your paper. You would have looked at it graphically. So you would have ended up plotting sine, you would have ended up plotting tangents and cotangents, and then you would have drawn a circle and tried to see where you can get an intersection. And those intersections that you have from your odd and even wave functions would be the eigenvalues. I will repeat this point again. I know it's a little bit confusing when I say it out without a diagram. I will repeat this again. So the even wave function that you have, or the even solution, which has no odd or sine components. Okay, so an even parity wave function that exists, E satisfies this particular equation. Note, this is not the wave function. Okay, not the wave function. Please don't get confused with that. This is not the wave function. This is the transcendental equation that would help you get your energy eigenvalues for your bound states, your EB, for your bound states. This is not the wave function. This is the equation, or the transcendental equation, that would help you get the energy eigenvalues for your bound states. Let's be very clear on that. So here you have a tangent. Okay, what would your odd wave function look like? The wave function for the odd solution has no cosine components, no even components, and therefore it would look like this. You would have a cotangent instead of your tangent. Okay, now these equations that you have are very difficult to solve analytically. Okay, the wave functions are very difficult to solve. So what you can do is you could try to solve this using either a graphical method or numerical method. You would have drawn a graph preferably like this. Wait, let's just step back a moment. Okay, so before I show you the graph, let's just look at this. The energies of the bound states that you have, E is minus EB, which is less than 0. These are well within the solutions of your transcendental equations. So what you need to remember is this, okay, like I showed you in the last class, last slide, sorry. What you need to remember is this, okay? So you need to remember this. This has to be committed to memory. And also you have to remember this for your odd thing, okay? You don't have to remember all the history behind the stuff. What you need to remember is these two. And what are these going to tell you? These are going to tell you the eigenvalues of your infinite square well potential. Okay, so now when you would have done this, you would have noticed some kind of a h bar factor that comes up all over through here. Okay, there would have been a h bar factor all over through here. Now, we're not going to be taking that in consideration. Usually, I don't know if you've seen this, but they do approximate some say particle physics, they do approximate your h bar to be 1. Okay, so I do not know if you've seen this, but here our intention is not to, we're not doing particle physics as such right now. So our intention is basically to just solve this numerical, problem using numerical methods. Okay, so you could choose your h bar equal to 1, and this has to be mentioned when you write the problem. Okay, so the problems that are going to be given to you are very generalized. Okay, they would just say explain using your bisection method, explain a physical problem. So they won't even tell you what the problem is. So you need to be able to write this in a way. It's a very, I know the question is a very raw question where you don't have anything specified to you, and you have to bring up yourself to try and formulate the problem. Okay, they won't really tell you that, okay, do it for an even bound state or do it for an odd bound state. You're supposed to be writing these approximations and saying you are doing it only for an even wave function, and you're doing it for, say, h bar equal to 1 and 2m equal to 1 and so on. Okay, you will see that once we start off with the problem, that I do approximate 2m to be equal to 1. Okay, so this is something that you would have probably seen, I'm hoping. Okay, so you would have even your even wave function gives you the tan KL solution, your odd wave function gives you this. Okay, and the intersection would tell you the number of bound states that you have. So if you have, let's say you usually this can be done in terms of a circle as well. So let me just say this. Okay, so there are different ways to approach this particular problem. One is this. The other way would be, you would be, say, given a graph, you would draw these sine and cosines and stuff like that. Okay, so let me just put an even wave function here in the middle. You would be given stuff like this, but you will draw a circle instead. So you would say, if you do have something like this, you would say there is two even bound states and one odd bound state. So that would how the whole problem would be. And as you increase this radius of the circle, and if you have, say, another guy coming up like this, so you end up having more and more bound states which are even and odd coming into the picture. So that's how we would solve this. Okay, you would have at least when I did it, we had an equation of a circle, and then we would have your tangent and cotangent. This is another way to do it, where you would, it's basically altering the formula that you have. And this is not something that you really want to look into, but I want to just give you the idea of what we are doing here. Okay, you really don't have to remember all this stuff. All you have to remember is those two equations that I told you about, and then you use the bisection method. but you do have to explain about the problem, and you do have to say that you're using a finite square well, you're using a finite symmetric square well. So symmetry, basically you end up having your even functions, even wave functions and odd wave functions, and you're choosing even wave functions in particular. So you would have to explain that, but you don't have to draw all these plots and stuff like that. Okay, so we discussed this before. Analytic solutions are hard to obtain for the infinite square well. Please be careful. Okay, I have introduced a little bit of a trick here. Okay, analytic solutions are hard to obtain for the infinite square well. So is it true or is it false? I will start the poll now. Okay, so analytic solutions are hard to obtain for the infinite square well. It is tricky and it can be missed. Please poll in your answers fast. You're too slow today. Last class, you guys were like really super fast. 30 seconds left. Ten seconds left. Please poll in your answers fast. 7 more of you are left to poll. Okay, I'm going to be ending the polling now. Okay, so I share your results. Analytic solutions are to obtain for the infinite square well. Is it true or is it false? The answer is false. You guys must have heard that it is hard to obtain analytic solutions for your infinite square well. We have been discussing about the infinite square well. You can use your graphical or numerical solutions for your finite square well. Okay, so let me just make this a bit clear for you guys. Stop sharing results. Okay, and let me just close the poll. Okay, so what have we been doing? What are we actually doing? We have been discussing about the infinite square well for quite some time, and I told you that you can either sorry, we've been discussing the finite square well. Sorry, it can be really confusing. Okay, we have been discussing the finite square well, and those are the problems that we're going to be solving. And I told you you have bound states and scattering states for this finite square well. Okay, so what do we have here? You can solve it graphically, or you can solve it numerically. And graphical solution is what you did in your first sem. What are we going to do here? We're going to start solving this numerically. Okay, ideally it should be done in a computer, but we're not doing that right now. Okay, so what do you mean by analytic? Analytic basically means exact solutions. Okay, and for the infinite square well, if you remember, this is basically a particle in a box. Okay, so what were the energy eigenvalues that you had? E sub n is equal to n squared pi square h bar square divided by your 2m a square, a being the width of your well. Okay, so this is the first thing that you learn in your quantum mechanics class. You learn about free particle in a box. Okay, so what do you have here? You can obtain analytic solutions. You can obtain analytic solutions for your infinite square well. Wait, I get confused with these true or false questions. Okay, you can obtain analytic solutions or exact solutions for your infinite square well. So it is not hard, it is false. Okay, so I hope you get that. How many of you answered? Let me just share the results. Okay, so majority of you answered said true. Okay, it is not hard to obtain it for an infinite square well. We just saw that here right now. It is very easy to obtain it, so it is false. Somebody in your class told me true or false questions are very hard to, answer, because there must be a small thing in your true or false question that must be like, really if you alter a small thing in your true or false question, you end up having issues. So what we've been discussing is finite. And if I make it infinite, it becomes very hard. So this is true. If I say that analytic solutions are hard to obtain for your finite square, well, it is true. Okay, let's move on to the numerical methods. Okay, so first, what do? We discuss about your bisection method. Okay, so your bisection method is also called the Bolzano method. I don't know if you've heard that term. It's also called the Bolzano method. Now, the bisection method, what does it do? It takes the midpoint of the interval as a new guess, x, and so each step basically reduces the interval size by 1. So there are 4 steps that are basically shown in this particular plot. So let's do that. Let's do this step by step. So say you have your f of x that you have here, and it's basically positive, right? It's in the positive relation. And here you have f of x, which is negative. So this is in the negative part. So +1, basically this plus refers to your function. So the function is positive, and this is the first iteration that you have. Negative basically says that the function is in the negative part, and this is the first iteration that you have. So what do? In this interval, you know that there is a root because you have a positive and you have negative f coming up. So you bisect that interval and you end up getting the value of that interval at this point. So when you calculate it for x2, or the second iteration that you take, you have a negative value of the function. So the function here is basically negative. So you know that you're supposed to be taking the positive and the negative. So the root is always between the f of x being positive and f of x being negative. So then you repeat this whole thing. You take you bisect this part, you bisect this region that you have, and then you get a root again, which is negative. And then you keep doing that over and over again. So you get something that tells you that f of x is coming very close to 0, but it does not exactly become 0 unless, of course, you have a very simple function. Unless, of course, you have a very simple f of x, it does not become 0 exactly. Okay, so you choose your x, you bisect that particular interval, and you choose your x such that your f of x tends to 0. Not exactly 0, but tends to 0 for complicated transcendental functions that you have. Okay, so now that we covered it, let's come back to the problem. Okay, so I told you what? I told you to remember that this particular equation is what you need to remember. You've equated your h bar to be 1, so let's neglect that. Now what do you have? You're given that 2m is equal to 1, a is equal to 1, p0 is equal to 10, and find several bound state energies EB for your even wave functions. Okay, so ideally when you're doing it for the first time, you do a graph. You try to solve it graphically so that you can get an idea of where the roots might be, so that you can pick up points where your function is positive and function is negative, and then try to bisect that. Okay, what do you have here? You substitute your 2m, you substitute your a as 1, and you substitute v0. So it becomes a really simple function. So you just have your function of EB. Okay, so what do you need to find? You need to find the values of EB that you have. So let me just show you how to do this problem. Okay, you need to get an idea of what your function looks like. That means you need to plot them. Now, obviously, you're not going to be given a situation where you're going to encounter this problem in your paper, because the thing is that we're not using computers to do this. We're doing this by hand, although we're supposed to be doing this using computers. The syllabus is framed in such a way that you have to do this by hand. So you're not going to be encountering this exact or altered parameters. You're going to be given a general question to just explain using your bisection method how you can solve a physical problem. That's what you're going to be given. That was one of the previous questions, actually. Okay, so first things first, you need to get an idea of what a function looks like. For the present problem, how do you do this? You basically make a plot of root of tan minus EB tan, root of 10 minus EB, tan of root of 10 minus EB minus root of EB is equal to 0 versus EB. So let me just go back and show this to you. So what you've done is, this is your equation that you have. You've just taken this root of EB to this side, okay? And then you've written that as f of EB. So there's nothing really to be confused about this, I hope. from your plot, you need to approximate some particular values. So you need to say, when is your f of EB going to be equal to 0? And the other thing that you have to note is your tan function tan or cotangent can blow off to infinity a lot, right? In a very short time, it can blow off to infinity. So what you need to do is you need to be very careful about that when you're doing this by hand. But this is not what is expected of you. You don't really have to do this by hand. If you're using a computer, you would end up plotting these values easily. So your idea is get an approximate idea where the function is beforehand. So basically, you're preparing yourself for this particular question before you go into the exam hall. That's what you're doing here. Okay, so let's just look at this. So once you plot these functions, you realize that there's going to be a root somewhere between 0 and 1, and there's going to be a root somewhere between 8 and 9. Okay, let me just blow up these two particular sections for you. So once you blow up the first part, you realize that's a root between 0 and 0.05. Okay, you realize there's a root between that, or you realize there's a root between 0 and 1. So that's very easy for you to identify. You don't have to like really go into very minute details and search this out. And then there is a root between 8 and 9. So, and these are the exact values which we should be able to compare it later on. So this is 0.00402 and 8.593. Okay. So once you've done the plotting and you've kind of got an approximate idea that it is between 0 and 1 and it's between 8 and 9, then you know what to do. You've done this bisection method a lot of times. So there is a root between 0 and 1. There is a root between 8 and 9. I'm going to be sticking on to 0 and 1. Okay. So 8 and 9, I'd probably give it to you as homework. You can try that out. So for me, it took about 9 to 10 iterations to get the actual values coming up. Okay. When I took 0 and 9, if I took 0 and 0.5, say, it would be a lesser number of iterations that I need to have. Okay, so what is your first step? Your first step is you put f of 0 into this function. Okay, so you put 0 into this function and you get some value which is positive. You get f of 1 and you put 1 into this function, 1 as the value for EB, and you get a particular value which is negative. So you know that there is a root between 0 and 1. Okay, so let me just repeat this point out again. Let's say that f of x is negative at x minus and positive at x plus. So the function changes from your positive to negative as x increases. We start with this interval, x plus less than x minus, within which we know that there is a 0. So once you get to know that there is a 0 between your interval that you've chosen, you bisect the whole thing. You write x is equal to x plus x minus by 2. Okay. Now this is your first iteration. So in your first iteration, what did you find? You found a negative value for your function when you put 0.5 here. So you know that when you put 0, what did you get? You got a positive value. Let's just go back and review that. When you put 0, what did you get? You got a positive value. When you put 0.5, what did you get? You got a negative value. So you know that your root is between 0 and 0.5. Let's just do a second iteration and then I will skip off to the 9th. So what do you have here? When you start to bisect the interval between 0 and 0.5, you get 0.25, and then you find f of 0.25 and you get a negative of the function that you have there. Okay, so then what do you know? F of 0 was positive, f of 0.25 is negative, so you know that there is a root between 0 and 0.25. So we proceed on like that. Okay, so 6th iteration, the 7th iteration, you're still getting a negative value. And then the 8th iteration, you start getting positive value. And then let's look at this. So let's look at the 9th iteration. Okay, once you substitute this function that you have here, what do you get? Finally, you end up knowing that there is a root between 0.039025 and 0.0585. Okay, once you bisect it, and finally you get something like 0.048828. So this is pretty much that is required. Okay, so you got a 0.004. What was the value in the problem that you saw? You had some 0.0041 something like that. So it's accurate to about the 3 decimal places, and that's all you need. So you found the first bound state approximately. You don't need the exact value. That's not the intention of doing bisection method. You're not looking for the exact value. What you're looking for is a approximate value. So you have a 0.004 here. Okay, so now I want to discuss something, some particular insight into this problem. Okay, so pay a little bit more attention here. You knew how to do the bisection method, so that was pretty easy to do. Let's just look at this. So the 10 in the value that you had, what was it? It was basically your V naught, the depth of the potential. Okay, so V naught was put as 10 in the previous equation. So this is basically proportional to the strength of the potential that causes your binding. Okay, so now if you make the potential deeper, okay, what happens? What happens if you change your 10 to a 20 or a 30 or a 50, or what happens? So what happens is basically the number of bound states that you have. Earlier you saw that there were only 2 bound states that I showed you in the plot. The number of bound states that you have increases based on your potential. So if you increase the depth of the potential, what happens is the bound state increases. Also, the values of the bound states that you have, the actual eigenvalues of the energies that are associated with the bound states are going to increase. Okay, so what I want to do now is I want to switch over to an animation. Okay, once I switch over to the animation, yeah. Okay, so we looked at V naught equal to 10, right? Here we looked at V naught equal to 10. So let me just try and get my mouse here. Yeah. Okay, so we looked at V naught equal to 10. Okay, and what did we find when we enlarged this particular thing? We found we had 0.004 here as one of the eigenvalues, and you had an 8.593. Okay, well and good. Now let me just decrease the size of this. Okay, so as you increase your potential, what do you see? As you increase the potential, you see that the number of bound states that you have increases. And not just that, okay, not just that, the actual values of the bound states that you have, they keep increasing. So look at this. This is going off to some 97 instead of the 8.5 that you had earlier for your V naught equal to 10. The energy eigenvalues of your bound states start to increase. So let's just play this back. So as your potential depth decreases, the number of bound states that you have decreases. Okay, I will repeat this again because there's a question that's coming up. Okay, so what do you have here? When your potential is 20, your V naught is equal to 20, almost approximately 20. What do you have here? You have 2 bound states. The bound states that you have are larger in the energies associated with the bound states are larger. Now, if I increase it further, what do you have? You start seeing more number of bound states that are coming up, and the energies associated with those bound states are also going to be larger in comparison to the V naught equal to 10 that you had earlier. Okay, so I will just show that to you again. Okay, so what do we have? With the increase in your potential, the number of bound states that you have increases. Also, the values associated with the energy, all the energies that are associated with the bound states also increase. Okay, so let me stop sharing this. Let's go back to our presentation. Okay, now what do we have here? Let's just go to the question. Okay, so as the potential increases, the bound states increase in number, the bound states energies increases, the bound states decrease in number, the bound state energies decreases. This is a multiple choice question, so please, you will have more than one choice that is correct. Okay, so let me just start off with the poll for that. I hope you can see the question. So please pour in your answers. As the potential increases, the bound states increase in number, the bound states energies increases, the bound states decrease in number, the bound state energies decreases. And we just discussed that a couple of minutes ago. So you should be able to plug in the correct answers. Wow. Somebody said the bound state energy decreases. You have 30 seconds left. Why are you guys not voting? Like more than half of you haven't voted yet. 15 seconds left. I told you more than one option can be correct in this case. I will give you 10 more seconds and I will stop the polls. Okay, I'm ending the polling. Okay, so yeah, most of you, yeah, 25 of you guys said bound states increase in number. Okay, so as the potential increases, I just showed you that as the potential increases, the bound states that you have increase in number. And you also said that the bound state energy is increases. So yeah, that's fine, but I don't understand like why the rest of you didn't get that particular point. Okay, so towards the end, if you want me to repeat that again, I will repeat that. For now, I'm just going forward because we are running short on time. Okay, we started 15 minutes late and we're still running short on time. Okay, so let me just, did I share the results with you guys? I hope I shared the results with you guys. So this is what you guys have answered. Okay, so let me just stop sharing the results and let's go on. Okay, so we've done with the bisection method. Now, the next thing that you have is your Newton-Raphson method. Okay, so what does the Newton-Raphson method do basically? The Newton-Raphson method takes a new guess as the zero of the line tangent to the function f of x as at the old guess. Okay, so you have some kind of a guess you need to start off with. You need an initial guess. Without the initial guess, you can't really start off with the problem. And when what do? You draw a tangent to the point at which you had your initial guess. Okay, so what you're basically doing is you're taking the function at that particular guess that you had, say x is your guess. You're taking f of x, and at that particular point, you're saying, okay, fine, this is not a curve, but a tangent to the curve that you have. It's a line that is tangent to that curve at that particular initial guess that you have. So that's the whole idea about your Newton-Raphson method. So this is how your Newton-Raphson method is. And this is a very good method because of the convergence is, if your root is quite close, you have a rapid convergence. So you get a convergence only like 2 steps rather than like 10 or 19 steps that you use to get your bisection method results. You have a rapid convergence in this case. Okay. So the Newton-Raphson algorithm finds approximate roots of the equation f of x is equal to 0 more quickly than the bisection method. This algorithm is equivalent to drawing a straight line. Please pay attention to this because there's a question. This algorithm is equivalent of drawing a straight line, f of x is equal to mx plus b, tangent to the curve at x value, that is the guess that you've started taking, okay, for which your f of x is equal to 0. Then using the intercept that you have, x, so basically what you have here is if you divided by your slope, what you would have here is a b by m. Okay, so you have a minus b by m of that line with the x-axis as an improved guess for the root. Okay, so let's just go on to this. Now, if the curve were straight, the answer would be exact. So if you're doing this for some function like a linear function that you have, like t, so I think we've seen a couple of other linear functions, say xt that you had before. Okay, so I think you had something like that where you did a linear approximation for your Gauss-Legendre integration, right? So you had something like pt plus q was your x, right? This was the thing that you use for your GL integration for when you had limits involved. So let's just, that's probably a pretty good review of that. Okay. So now this whole thing continues till some level of precision is reached. And then what do? If your guess is in a region where f of x is nearly linear, then the convergence is rapid than the bisection algorithm. Okay, so let me just start off this poll. And then I will read the question because I don't want to lose time on this. So yeah. In the Newton-Raphson method, the function is approximated to be a straight line tangent to it. Is it true or is it false? Please poll in your answers fast. We have 10 more slides left, so I just want to be pretty quick. Ten more seconds. Not giving you much time on this. Why would you answer false? We just discussed that. Also, you would have learned this in your second semester quite thoroughly. You would have also learned this in your BSc. So okay, I'm going to be ending the polling now. Majority of you answered true. 5 of you answered false, and I don't know why. In the Newton-Raphson method, the function is approximated to be a straight line tangent to it. We just discussed that, and we kind of like showed that you're looking at the tangent, the straight line tangent to the initial guess that you applied onto the function f of x, right? We just discussed that. So I will stop sharing the results and I will move to this. Okay. So what you need to remember is this. Okay, so basically I would write a general equation for this. X1 is equal to x naught minus f of x naught divided by f prime of x naught. F is your single variable function defined for a real variable x, and f prime is the derivative of that. X naught is your initial guess that you use for the root of f. Okay, so this is the more general formula. Xn plus 1 is equal to xn minus f of xn divided by f prime of xn. So what is the problem in this? You can't use it for a function where your derivative goes to 0. Okay, you can't use it for a function where your derivative goes to 0. Why? Because if the derivative goes to 0, this ends up becoming 0 and this whole thing blows up. Okay, so it becomes minus infinity. It blows up based on what kind of a function that you have, or based on the value of f of xn. It goes to minus or plus infinity. Okay, so again, we have the same problem that we looked at. We looked at for even wave functions. Okay, so your 2m is 1, a is 1, b naught is equal to 10 for several bound state energies EB for your even wave functions. You need to find several bound state energies. Okay, so what do? You substitute all of these values that you have, and then you write your f of EB is equal to 0. Okay, now the trick here is this. Okay, the issue here is calculating this whole thing takes a humongous amount of time. It probably takes pages and pages of calculation. Okay, so how do you calculate this f prime of EB without having to explicitly find out the derivative? Okay, there is a trick to do that as well. Okay, so I will explain about the trick, but let me just explain to you how this Newton-Raphson method works, which you should probably be knowing. So first, ideally, what you would do is calculate the derivative of the function EB, okay, where you have this, and you need to find out this result. Okay, so just as an exercise, I'm going to be giving this to you as a homework to do it. Okay, I do have the solutions with me, which I will share later on, and probably we could do a session on just solely homework. But this would be the homework for your lecture 5. Lecture 4 had no homework. Lecture 5 has a homework. So you had only 4 homeworks so far. Lecture 1, lecture 2, and lecture 3 had homeworks, and I think you would probably be done with 3 today. Lecture 5 would have another homework, which is to calculate the derivative of this function f of EB. Okay. So after you for finding this derivative, okay, it is really hard. It's not very easy to do it, and based on the function that you get, you have to keep repeating the whole thing. So there's an alternative way to do this rather than looking at, you know, the exact or the explicit values of the derivative of the function. We can use the basic definition of a function. Okay, so let me just go through this. Finding the derivative and doing the problem is quite hard. Okay, it's quite cumbersome. the Newton-Raphson method algorithm requires evaluation of the derivative f of x by f df by dx at each value of x naught. In many cases, you may have an analytic expression, but for more complicated problems, it is simple and less error prone to use numerical forward difference approximation to the derivative. And this is probably something that you might have encountered in your 12th grade. Okay, so it's basically f prime of x is equal to f of x plus delta x minus f of x divided by delta x. This is the initial thing that you learn when you're learning derivatives. Okay, so when you're learning derivatives, the first thing that you learn is I take a small value of your delta x, I apply it to the function, subtracted it from the f of x that I have, divided by the small value. Okay, delta x is some small incremental value of x that you choose. Okay, it does not have to be given to you, it's something that you choose. But there is an issue here as well. Okay, be very alert now. There is an issue here as well. The delta x that you use cannot be equal to the increment that you're using. Okay, so let me just show you that. It should be different from the delta x that you have here. Okay, so delta x is equal to delta xn plus 1 minus xn. Okay, the point, it should not be the difference between the initial guess and the next guess. Okay, so this is your, let me just write that down. So if you have x naught as your initial guess and you found that the next point is x1, this delta x that you have cannot be equal to the difference between the initial guess and the next guess, next obtained value based on your initial guess. Or yeah, that would be more way to write it, because the next value is not a guess. The next value is something that you obtain based on your initial guess. Okay, so I hope you get that point clear. Delta x cannot be equal to this capital delta x. Okay, so now once you've done that, okay, this is basically your problem. This is your f prime of EB that you have. Okay, so this is a standard way to do it using your, what do you call, using the derivative. So here, what we've actually done is use the actual value of the derivative. And I will be showing you a way to calculate the derivative just for this one, okay, without having to actually calculate it. So this is something that you know how to do. X1 is equal to x naught minus f of x naught divided by f prime of x naught, and you substitute this and you get it. Okay, now we're going to be looking into the alternative way to do it. Okay, so I'm sure you're able to do something like this. All that is required is you have you just substitute plug in the values and substitute it, and then you get your x1. And then you take this x1 and you would plug in it for the next one. So this would be x1 minus f of x1 divided by f prime of x1. Okay, so you plug it into the next one and you get your value here. For your x3, you plug it in and you get your value here. Okay, so let's go on to the trick that you have. Okay, so here you have an f prime of x, which is equal to f of x plus delta x minus f of x divided by delta x. So delta x is some small change in x that you choose. Again, I'm reiterating this. It should be different from the capital delta x that you have. That means it should be different from x1 minus x naught if you're doing it for the first time. Okay, if you're doing it for the first iteration, it should be different from x1 minus x naught. Okay, so let's assume that the value that you have for delta x is 0.0001. Okay, so if you assume a very, very small value, then all you have to do is you just have to apply this to the function that you had earlier. You don't have to calculate the function. Just apply it to this function that you had. What is this? Yeah, this function that you have. So you take that 0.005 or whatever plus 0.0001, I think, yeah, 0001, and then you apply it to this. So you have to calculate f of this. That means you don't require this guy. Okay, this guy is not required. So you just have to use the basic definition of that and calculate the value. So once you do that, what do you find? You find that this value that you get, your f prime or the derivative, is quite similar to the value that you got earlier. Okay, so this is minus 7.5709. What did you get as the exact value? You got minus 7.57441. It's pretty close. It's pretty good. Okay. to do. So it's about 2 decimal places, and this is pretty good enough. There is going to be a small error, but it's pretty good enough. Similarly, you do it for the next one. Okay, so after you do this and you calculate this up, you do it for the next one where you have your x2 here as 0.004019. So once you calculate your x1 and x2, you know you're pretty much close to the value that you actually got. What was the value that you got? You got some 0.004 and something like 1 or something like that. That was the actual value that you got for your eigenvalue, and this is what you get here. Okay, so let me just tell you what the questions are going to be like. These are one of the previous year questions that you have. They will just ask you this: illustrate the bisection method of numerical solution by considering a physics example. They haven't told you about your quantum states in a square well. They haven't told you about anything. And if you just take a random example, and this is a 10-mark question, okay? So you need to be able to start explaining from scratch, like about the quantum state, what type of well that you're using, and then you need to start shortening stuff up. But you would have to also solve this numerically. Okay, so basically you have the answer pre-prepared in your mind and you have to apply it and write it down. So with this, we are at a wrap. The entire syllabus is completed.